I get started. Last class and this class, we're talking about feeding data, analyzing data, plotting data, simulating data, and it's basically our introduction to data science. And like the coding work we did last week, the data work we do this week is kind of the foundation for the remaining weeks of the semester and the physics problems we're going to tackle there. In the last class, we focused on reading data, various ways you can read data in Python. And we also focused a bit on analyzing data, for example, using tools to calculate averages and standard deviations and variances in Python. In today's class, I'm going to focus on visualization of data. We're going to talk about matplotlib and different ways to visualize plot data. In the previous class, I just drew on an example kind of outside undergraduate or graduate physics problems from climatology about the temperature of the Earth, and I was able to write down a simple difference equation for the temperature of the Earth, and we work with that. In this class, I'm going to take another problem that's from completely outside our sort of undergraduate or graduate physics education. It's from ecology. It's about populations, survival of populations. It might be rabbits, it might be humans. Again, I'm going to write, knowing nothing about it, I'm going to write a difference equation for population of rabbits or a population of humans, and we're going to use that as a basis for exploring, plotting, visualizing data. And again, it's going to be a difference equation. Okay. So, as I mentioned, in science or in physics, we want to visualize data. We do it via various categories of visualization tools. We make graphs of data. We make histograms of data, we make diagrams of data, we make videos of data. And so these things are used to further deepen or enrich our understanding of the data. I'm going to focus on this package, matplotlib. That is a Python package. That's a very comprehensive Python package for plotting. I'm just going to cover in today's class a few common examples of visualization of data with matplotlib. There's a huge world, a huge gallery of examples of plotting, visualizing data with matplotlib. You can go to this link here. I'm going to look at the sort of most common things we would do with physics and data. We might want to plot measured data itself. We might want to plot data that's in arrays. We might want to plot functions. In doing those things, we typically might use line graphs to plot data. We might use scatter plots. We might use histograms as ways of plotting data. So I want to cover those things. I won't go at all into all the details of how you beautify your graph, your matplotlib graph, or beautify your histogram in matplotlib. I'll just say a few words about titling histograms or plots, labeling axes on histograms and plots, the markers on the plots, the lines on the plots to get us going. But it's a whole world that I feel I'm only the tip of the iceberg on. Okay, I'm going to skip these slides, move from the slides now, and just go to some examples of code of plotting, and then we'll turn to my ecology example of the survival of rabbits or the survival of human beings and the difference in equation and some plotting related to that. That was my Physics 508 directory that we started in the first class. And I added a few little notebooks to it for different examples of plotting. I'm going to make this bigger because I know it's too microscopic. In this first example that I've made is I happen to have a data file that contains some data on projectile motion. Actually, it was 2 columns on data on the vertical elevation, vertical height of a projectile versus the elapsed times for that projectile. Let me just show you what the data was. It also is in here. This is this file here. So it just contains two columns of data. The vertical height of the projectile was measured roughly every 3 milliseconds. So I think it was it no 30 minutes, roughly every 30 milliseconds. We got a measured height of the projectile as it was thrown from the ground upwards and then fell back downwards, and it went up to a height that was just over 10 meters. So I got this data in this text data file, and I'm going to read that data in with this. I'm going to read the data into 2 arrays that contain the kind of the independent variable, time, and the dependent variable, the vertical height of the projectile. This little bit of code to read the file, read the data into these 2 one-dimensional arrays, I just copied from an example from last class, because we were reading data from a file in the last class. And so this little fragment of code, I simply just cut and paste it from the last class. But if you look at it, again, to read data, if I've got a Google Collaboratory notebook, to read data from your Google Collaboratory drive, you need a Google package to integrate the drive with the notebook. And specifically, you call a function drive in that mount in that package to integrate your Google Drive with your notebook. So that's what I've done here. Then reading the data is just specifying the location of the file, its subdirectory and its file name. And then I'm calling a high-level function to read data from a file. It was in the numpy package. It was the load text function, and I just gave it the file location. I had to tell it that there's this one header that I put in. But anyway, it read the data into a numpy array. This stage is a 2-dimensional numpy array, 2 columns and many rows of data. And then I sliced it. We talked about slicing last time. And I use slicing here, like we used last class. I sliced it out into the 0th column for the dependent variable time in the second, but column 1, index 1, for the vertical height. Okay, so nothing new there. But this is newer. This is where I'm going to, using matplotlib, which is a Python package like NumPy was a Python package, which I've imported, like I imported NumPy as a Python package with an alias NP. I imported actually a module within matplotlib, and I've aliased that to plot. And so I've got this package imported, and I'm just going to use it like I've been importing NumPy and using it. And it's very simple to make plots in Python. It's very straightforward to make the plots in Python, just using a few of the matplotlib functions. When I make a plot, I'm going to make it kind of on a canvas. Imagine a canvas for a painting. I'm going to make have a canvas for my plotting. and that's referred to as the figure here. And then within a canvas, you could have one plot on your canvas, or you could have multiple plots on your canvas, and you could determine how many plots on the canvas, how you're going to arrange the plots on the canvas, the size of the plots on the canvas. So this first function here is really just to, I'm using it just to set the size of the canvas. So those dimensions 8 wide and 5 high are going to be the dimensions of my canvas on which I'm going to put my plots. And so I'm defining that, and then the actual plotting of what we're interested in, which is the vertical height of the projectile versus the elapsed time for the projectile, is just by this function plot within our matplotlib library. So I just call that function here. Again, there's a lot of arguments. I'll just say a few words about a few arguments here. The first pair of arguments are the independent dependent variable. I've got a set of XY points in 2 arrays. So the first argument is the independent variable, the time array. The second argument is the independent variable, the Y array. And so that I want to plot Y versus T. So I'm saying that. This little string here, this is like the code word for the line style or the marker style that I'm going to use in making the plots. First of all, I could make a plot that was a series of points, or I could make a plot that's kind of a connected line. The dash here is for a connected line. If I had a period there, would be for a series of points. So that's why I could do a line graph versus a series of points graph. The character, the B, is for the color of the line or the point. So B for blue, obviously, what's R for? R is for red, and so on. So this is a very basic way of saying, you know, what style do I want, line graph or points, and you know, what color are the markers or the line. You know, you might have a graph that has multiple sets of points on it or multiple lines on it, and you might want to label the different sets of points on the graph or the different lines on the graph. So you can label your particular pair of coordinates, and so I'm just going to label this pair of coordinates as the height versus time data. So that's all on that as arguments in the plot function. And as I say, there's a lot of other arguments and a lot of detailed things that you can do with the plot function arguments. That alone, I've got to make it smaller now, made this plot. So you see time, the horizontal axis, as the projectile's in the air for 3 seconds now. And then the height, the projectile went from the ground to 10 meters above the height. And so here is the graph that represents that. Here I drew a blue line graph. I mean, I could have drawn a red series of data points, and it would look like this. And as I say, if we'd had several projectiles, I might want several sets of data points or several line graphs, and I might want to label them. So I labeled these red points with that height versus time label. There's a couple of other things that we also want to title our plots maybe and label our axes on a plot. So these couple of lines here are just the titles the plot. X label labels the horizontal axis. Y label labels the Y axis, and so on. And calling legend actually draws this legend. Okay, so that's one type of plot that we would often make. There's another type of plot that we would often make, maybe not in this context, it's a little bit fake for me to make a histogram in this context of this data on this projectile, but I did make a histogram, right? Often we make histograms of data where in each bin of the histogram are the number of events that have that value, some value corresponding to that histogram. We might make a histogram of scores in an exam, right? When I taught general physics, I always make a histogram with the distribution of scores in the exam, where maybe I've got from 0 to 100%, and maybe I've got bins that are 5% wide. And so there's 20 histograms, and I've got a nice curve of the distribution of scores in the histogram. So that's a common thing we would do with data. I try to make a histogram for this data here. What I did was make a histogram that corresponds to how many data points did I have for the projectile in the first 2.5 meters of its flight above the ground? How many points did I have in the next 2.5 meters, from 2.5 to 5 meters, next 2.5 meters from 5 to 7.5, and then the final 2.5 meters from 7.5 meters to 10 meters. I just wanted to plot how many data points I had in each of those, how many measurements I had in the projectile in each of those little intervals. Look, the projectile slows down as it goes up. We know that. Because we did gravity last week, and it speeds up as it comes down. We know that. So I'm going to have more data points in the bin corresponding to the 7.5 meters to 10 meters, the highest elevation of the projectile, because it's spending more time there. I'm going to have the least data points in the bin that corresponds to ground level to 2.5 meters, because it's going fastest there. There's the least data points there. So I was going to make that histogram. Again, I'm doing this in a new cell, so I'm divining the size of a new canvas again. Now I'm going to make a histogram with a core, not to a function plot, but a core to a function histogram. But I'm going to do one thing before that. I'm going to define an array, and I'm going to define an array that is the edges of the bins that are going to make the histogram for. And the edges of the bins that I want to make the histogram for, remember the first bin was going to go from 0 to 2.5 meters. Next one from 2.5 to 5 meters. Next one from 5 meters to 7.5 meters. The next one up to 10 meters. So I've got five edges there, an edge at 0 meters, 2.5 meters, 5 meters, 7.5 meters, and 10 meters. And the histogram function core, if you want to specify the size of the bins and the range of the bins, you need to specify the bin edges you want. And so I'm going to define the bin edges that I need for my particular part of this particular projectile. And I did that with this line here. It's a line that defines an array of bin edges that I've called bin edges. Let me make it bigger. And it's defined with a numpy function that's called a range. And that numpy function, so this is a useful function for us. We'll use it and a similar function, lin space. I'll talk about that later. But we use these functions often to generate arrays of regularly spaced data. So this is one way of generating an array of regularly spaced data. In this case, it's the bin edges that correspond to the the elevations of the bin edges. The arguments for this function are kind of the lower range, the upper range, and you specify a interval, a step size through that range. So if you think about this, the way it's done it here, it looks like I'm going to define an array of bin edges that are 0. The step size is 2.5. So the next one will be 2.5. Then the next one is 5, 7.5, 10, 12.5. Well, why do I want the 12.5? I actually don't want the 12.5, but the way that A range works is that it's kind of an exclusive, you define an exclusive end to the array. Exclusive meaning that the 12.5 is actually not included in an array. So this array actually is an array not of 6 elements, including the 12.5, but an array of 5 elements that omits the 12.5 and ends at 10. If I was to print it, what is it? Bin edges. What am I doing? This is what we just made. So you can always check that you've made what you wanted to make, obviously by printing the bin edges. And I just made all the edges that we need. These are all the lower edges or upper edges of the bin. There's no 12.5 in there. Okay, then it's straightforward. I called the histogram function with the quantity that I want to histogram. You know, I've got some 100 measurements of the elevation of the projectile. I want to bin them into whether the measurements were in this interval 0 to 2.5 meters or any of the other intervals. So I want to bin them in bins defined by these edges here. So that's my second argument. And then there's beautification arguments. I've just said I'm going to make an orange histogram. And so we had run that, and here it is. Here's the 4 bins that we constructed with 5 edges that run from 0 to 10 meters. So this bin is 2.5 meters wide. This is 2.5 meters wide. Here's the I put duration here, but it's really the number of measurements, the number of array elements that correspond to those elevations. But it's a proxy for the duration that the projectile spends in each of those bins, because it's going fast at the bottom, it's going slow at the top. And so it's a proxy for the duration of the flight time in these different elevation ranges. And you see what you expect, right? The projectile's going slowest as it gets near 10 meters, and it's going to turn around. So we got a lot of measurements up there in that highest elevation bin. The projectile's going fastest when it's just left the ground, or when it's just about hit the ground in the lowest elevation bin. So we got the least measurements down there. And so this is a histogram. And again, I labeled its vertical and horizontal and vertical axes, and I titled it with exactly the same X label, Y label, and title functions. Any questions on that? In a way, those are the 2 most common types of plotting that we meet, drawing a graph and making a histogram. And they're very simple, straightforward in Python. Let me show you a couple more examples. That was data. I plotted data, discrete data. What about if we got a function? Often in physics problems, we have a function, a smooth function. Maybe we want to plot a smooth function. How am I going to do that? So this example, I just want to show you plotting a smooth function. And it's this again out of my 508 directory. In this little code, I'm going to define a function, actually a couple of functions, a couple of smooth functions, and then I'm going to plot those functions as if they were truly continuous analytical functions. So that type of plotting. Well, of course, again, Let me make this bigger. I need import my matplotlib and I import my numpy as the usual aliases that everybody uses. Now I've got the problem of I want a smooth function to plot. But I can't have a smooth function on my computer, my numerical computer. I can have arrays, but I can't have a smooth function. What I'm going to do is to define an array. I'll define an array for time, and then I'll calculate corresponding arrays for the position and velocity of a pendulum. I'm going to define an array that has it's going to have discrete times, but they're going to be so finely spaced that it looks essentially continuous. And that's how I would draw a function with matplotlib tools. So that's what we're going to do in this cell here. And this is where I mentioned that I'll use linspace. Now, in the last example, we used a range to I can't even remember what we used it for. Make the histogram big, wasn't it? Here I'm going to use linspace to also make an array of equally separated elements. This time they're going to correspond to the time rather than the height. So it's the height of the projectile last time. Now it's the time for the pendulum's oscillations. So I'm going to make a proxy for continuous time. That's going to be a discrete time that's made by a call to this linspace function, also in numpy. The arguments for that look similar, so that there's a starting time, there's an ending time, just like a range, but in place of a step size, there's a number of steps. So that's a difference between a range and linspace is specifying the number of steps versus the step size. And sometimes, you know, because of the problem, you want to do one or the other. So that's a reason to pick it. There's another difference, and I talked about it in the case of a range. It was the end of the array was exclusive. It didn't include the last data point. In linspace, it's actually inclusive. It does include the last data point. So there will be a data point corresponding to this stop time here. I have no idea why that is. Why linspace does it one way and a range does it the other way, other than to illustrate that there's two possible ways you could do it, I guess. But anyway, I can show you that if I just run this and print T. You see that it starts from 0, so that's the lower end of the range here. But it actually goes to 10 pi. This is exactly 10 pi here. And so it does cover the full range. It is inclusive, not exclusive. I actually said that I wanted to make the spacing between the points so fine that it becomes effectively continuous, a good proxy for continuous. So let me make this array much bigger. Let me make it 1,000 elements and go from there. So once I got the time array, I made two more arrays, time arrays that independent variable. I made two more arrays for the dependent variable, the position, called it y for the pendulum, and the velocity. I call that vy for the pendulum. So I'm making now two dependent arrays that correspond to the dependent variable. And they just I invented them as solutions of the damped oscillator. So they have an oscillating component to them, and they have a decaying component to them. So they have some sort of natural frequency. I'm plotting 5 periods of their natural frequency here. And then they have some sort of damping constant that puts them in an underdamped range. We talked about that before. Now, one point here is that if you look at those equations, if time had just been a floating point variable, then y and vy would also just be floating point variables, corresponding floating point variables for the position of velocity at that time. But time is an array. I made it an array of very finely spaced points. That makes y in vy, position and velocity, also arrays of very finely spaced points. So that's one of the nice things about arrays in matplot in NumPy. It understands if you're using equations in array, then the products of the equations, these two equations here, will also be array elements. Did you have a question at the back? Oh, I thought I saw a hand up. Okay, so I've got these arrays now, and now I'm just going to plot them. The plotting is the same as we did for the plotting of the data points for the projectile. So I'm just going to define a canvas here, but this time I'm going to define a canvas with a function that's called subplots. So it allows you to put multiple plots on a canvas. I just wanted to show you that. And it returns not just a object that is the canvas, but also an object that is the individual plots. So I poured subplots with the argument 2 because I want to make 2 plots. I want to make a plot of the position of the position of the pendulum and the velocity of the pendulum. So I want 2 plots. So that's the argument 2. It's returning a object that's a canvas, which is called fig here, the figure, and it's returning also a 2-dimensional array axes. So it has axes has 2 elements for the 2 subplots that are going to go in that canvas, in that figure. In the axes array element 0, in that object, I'm going to plot the position versus time, like we did before. Those are the first 2 arguments. Well, and in the second element of the axes array, that object, I'm going to plot the velocity versus time. And so that's what I've done here. Is my velocity versus time. Again, those first 2 arguments. I do a little bit of labeling. We met that before of the X and Y axes. I can give the whole canvas, the whole figure, an overall title with this function here, as kind of super title, to describe the fact I'm plotting in the 2 plots, both the position and the velocity versus time. And if we look at these, I'm going to run this again because I went from a coarse array of times to a fine array of times. These are my 2 plots. So this is the position of the pendulum versus time. This is the velocity of the pendulum versus time. We see the periodicity, we see the damping, we see them appear because the fine grain of the arrays as if they were continuous functions. And it's a way we might plot continuous functions in pipe. Any questions on that? I wanted to show you one last example before going on to human survival and starvation and reproduction. What am I doing? Yes. In this code, I'm deliberately not showing you the entire bit of code here. I didn't need to show you all the stuff that's common to all the other examples I've shown you. In this code, I'm going to plot the trajectory of a projectile that's thrown through the air. It goes both up and down and left and right. So it's a two-dimensional projectile motion. And I'm going to plot the XY trajectory. So I'm going to make a plot that horizontally is X and vertically is Y. So it's going to be a projectile motion. I calculated this time the motion of the projectile just using the equations of motion, the solutions to the differential equation that we talked about in last week. So I define an array of times here with Lin space. The range of the array I arranged to be the flight time or the duration of the flight for the projectile. So this is going to be an array of times that just covers the flight time of the projectile. And then using the equations of motion, I just calculated the X and Y coordinates, the X and Y positions as a function of time, my projectile, with the equations of motion. I put them both on one line. You said sometimes that's kind of convenient, maybe. So X and Y equal, here's the expression for the horizontal component of motion. Here's the expression for the vertical component of motion. Anyway, at this point, I've got the X and Y coordinates of the projectile, and that's all I want to plot. That's the main, that's where my start point really is. I've got a set of coordinates for the X and Y positions, the trajectory of the projectile. I want to make a plot of them. I could plot those on a graph that we made with plot. I could do that, right? I could just call plot with these arguments. But I've actually called one other function that I wanted to show you that we often use, and it's called scatter. It also plots XY points. So plot will plot XY points, scatter will plot XY points. You see scatter is not plot here. So why is there scatter and why is there plot? They both will plot a series of XY points. One big difference is that plot can draw a line between successive points that you're plotting. So I gave plot an array of XY coordinates. It could draw a line between consecutive coordinates. Scatter can't draw a line, doesn't draw a line between consecutive coordinates. So if you want a line graph, you've got to use plot. You can't use scatter for a line graph. So that's a big difference. A second big difference is that scatter is built to handle arrays of many data points, large numbers of data. So it's built for handling large numbers of data points, whereas plot is not built for handling large numbers of data points. It's built for handling relatively small numbers of data points. So if you've got a large number of data points that you want to make a plot of, a scatter plot of, do a scatter plot, not a plot plot, because it'd be much more time effective. The other thing about scatter is it's got a lot more tools for customizing the appearance of the scatter plot when you plot a series of points. Tools that aren't available in plot for characterizing a scatter plot type plot. So that's why I wanted to show you. But basically, the first two arguments again are the two coordinates that you want to plot. So I'm doing the trajectory here. So I've got X and Y. There's similar sets of additional arguments, but their notation is often different. And also, as I say, there's more abilities to customize and scatter. So I made the color of the markers blue. There's a size of a marker you can set in some units of pixels. I made that 10. You can do the labeling again, but let's just take a look at this plot. And here it is. It looks very similar to a plot that I made with plot rather than scatter. But as I say, I couldn't, if I'm using scatter, I couldn't draw a line between the points. And if I had a lot of data points, I wouldn't want to use plot. I would use scatter, and I'd have more flexibility in customizing the look of the plot. Okay. I think that's everything I want to cover on the plot function, the histogram function, the scatter function. Those are the three things we've visualized data with. We've talked about all the ancillary functions like labeling axes, titling the histogram, etc. There's bunch more, but let's go on to our ecology problem. What am I doing? So I want to set up a problem where we're going to do some plotting, some more interesting plotting. And we're also going to plotting of data. We're also going to do some simulating of data. I also wanted to take it from outside of physics, from just somewhere in science, to show that these tools of difference equations, differential equations, are applicable way beyond, just physics. They're applicable in biology and chemistry and economics and so forth. And so that's why we're picking examples elsewhere that we can solve numerically, computational, with difference equations problems in all sorts of fields with the tools we get in this class. Okay, so I want to think about population and model population. If you want a concrete example, imagine a field with a bunch of rabbits. Let's model the population of the rabbits in the field. Or maybe you want to think about the entire Earth and the population of humans, or you want to model the population of humans on the Earth. So that's our real life problem. We're going to make a model of that. Right? How's the population going to change? Well, reproduction is one way the population can change. That could cause growth in the population. And in my simple model, I'm just going to say that there's just a fixed reproduction rate, right? That's in proportion to the population. So the bigger the rabbit population, the greater the proportionally greater increase in population due to reproduction. So that's just a model, right? Then the population. That's the good news. Population could climb because the rabbits are living in the field, right? The field can support some number of rabbits from the food in the field. So that there's a capacity of the field. So I'm going to model the limited resources for our rabbit population as a sort of capacity for the field. So there's going to be a decline in the population, I said, if the difference between the total capacity of the field, i.e. the maximum population of the field, and the actual population of rabbits in the field. If that number gets small, we're filling up the field with a maximum number of population. That's going to cause a decline in the population. So I'm going to model growth and I'm going to model decline in rabbit populations by one being proportional to the population due to reproduction, and one being proportional to the gap between the capacity and the current population of the field, which is going to cause the decline. Based on that little model, I'm going to calculate, make some predictions about the population of rabbits in the field after many generations. And what we're going to explore, even within this simple model, what we're going to discover is all sorts of things happening within the model. We're going to discover simple cases where the rabbit population dies out, simple examples where the rabbit population is growing to some equilibrium. We're also going to discover rabbit populations that oscillate between two distinct values, or oscillate between four distinct values of generation after generation. These are called bifurcations. So we'll see these effects of rabbit populations oscillating between generations, and we'll also see chaotic behavior of the rabbit populations in the field, or the human populations on the Earth. So in this little model, there'll be all sorts of emerging effects that we'll discover. So this is one of the powers of computational physics for modeling these bifurcations in rapid populations, this chaos in rapid populations that you couldn't, you could analytically, you couldn't study this effect. And then we would, in reality, we count rabbits in the field and compare it to the data. I'm not going to do that. And yeah. Okay. I want to talk about what's called iterative maps or our difference equation. We use the difference equation for the temperature of the Earth, writing the future temperature of the Earth in terms of the current temperature of the Earth. We're going to use a difference equation here for the next generation rabbit population in terms of the current generation rabbit population. So it's the same sort of population. In general, that problem of the future generation based on the prior generations, or the future temperature based on the prior temperature, is a difference equation. When the future generation just depends on the current generation, only the current generation, that's often called an iterative map. And it's described by just a function, I put it f of x here, that tells you how to take the current population and map it to the next generation population. In the language on this slide here, it's going to, the current population is going to be xn. That's the population for the nth generation of rabbits, and it's going to tell us how to calculate the population of the n plus 1 generation of rabbits. And so that's what a iterative map does. So that means that if you start, let's start the rabbits out. Let's throw a bunch of rabbits in a field. The initial population of the rabbits is going to be X subscript naught. That's the 0th generation of rabbits. Then we're going to use the iterative map to calculate their children. So the next generation of rabbits, that's going to be X1. And then with that generation of rabbits, we're going to calculate the next generation of rabbits. That's going to be X subscript 2, and so on and so forth. We can just keep using this iterative map, this same formula, same equation to calculate generation, and generation. So that's going to be a kind of discrete scheme for calculating the future generations of rabbits. Of course, it is a severe approximation, right? Think about it for humans, right? To imagine that there is one generation of humans, basically, that all simultaneously gives rise to the next generation, and then that generation, the next generation. There's no overlapping of generations. That's not realistic. But this is this simple model of how generations propagate forward into the future for these rabbits. Okay. As I say, this is iterative maps is a big field. We're talking about it in ecology. It's common in biology and chemistry, in physics for different sorts of reactions. It's also in the economy, right? Stock prices from one day to another, or the economy from one day to another. You can build iterative maps. All those things came in generations, right? So you can build iterative maps. This would be perhaps the simplest iterative map of our rabbit population that just includes reproduction. And this would be what you would call a linear iterative map, i.e. the relationship between the future generation and the current generation is just linearly dependent on the current generation's population. So that map that I wrote down upstairs there, that the future population is R, a parameter, the reproduction rate times the current population, is a linear iterative map for future generations based on the rate at which rabbits reproduce. And you could see there, right, the larger the rabbit reproduction rate, then the larger the population will grow. The smaller the rabbit reproduction rate, the slower the rabbit population will grow. In fact, you can see that if the reproduction rate was less than 1, in this iterative map, then the future population would be smaller than the current population. And if that keeps going on, then the population dies out. The rabbits don't survive. If the rabbit reproduction rate is greater than 1, then the next generation of rabbits is larger than the current generation of rabbits, and so on and so forth. The rabbit population keeps growing and growing and growing and growing, and exponentially. And that it implies that there's no limit on resources for supporting the rabbits. And of course, there's limits on resources for supporting the rabbits in the field. So this is a simple map in which only 2 things really happen over the generations. Either if the reproduction rate is less than 1, the rabbits die out. And it's just a question of how quickly they die out, depending on the reproduction rate, or the rabbits, if the reproduction rate is greater than 1, just keeps on continually exponentially growing. It's just a question of how fast the exponential growth is, and that's kind of an unrealistic situation. So let's make a improved map, and the improved map over that simplest map is a nonlinear map compared to the linear map, and it's one that incorporates both the reproduction of the rabbits and population growth, but also the limited capacity of the field with the rabbits and population decline. And the famous map to, in simple terms, describe both the growth of rabbit populations and decline of rabbit populations is the map on this overhead here. It's non-linear because if you look at it, there's on the right-hand side, there's a linear quadratic term in the population of rabbits. There's also plus and minus signs, so there's reasons the population can increase and decrease from that. This will see models, basically models both these effects of increasing population from reproduction, decreasing population from the capacity of the field. So basically, the reproduction is in proportion to the population, and that will increase the future population based on the current population. And this term here, 1 minus xn. So this is the kind of the difference between the current population and the capacity population for the field. This is what's going to cause the rabbits to starve, the decline in the population. So the population becomes a balance now between reproduction and starvation. Let me just say a few words about the range of the parameters in this map. If you look on the right-hand side, there's R, that's a parameter, the reproduction rate, and there's XN, that's a parameter, that's the population. The units of population, XNs, are in the units of the maximum population of the field that contains the rabbits. So we think of XN, we're going to think of XN as running from 0 to 1. It can be anywhere between no population of rabbits or the maximum population of rabbits is 0 to 1. So it's not counting individual rabbits. It's this range of from nothing to the field's capacity. I'll show you on the next slide but the range of reproduction rates, I don't know why that's there. The range of reproduction rates for this kind of normalization here is the reproduction rates can be anywhere from 0 to 4. And it becomes unphysical to have a negative reproduction rate, unphysical to have not allowed to have a reproduction rate above 4. I'll show you what. This is kind of a picture of how that, or a plot of how that linear map works. Horizontally is the current population, and vertically is the next generation's population. So it's xn plus 1 versus xn. And the different colored lines are for different, there's a parameter in there too in the equation. They're for different reproduction rates. Let's just take a reproduction rate of 1, right? We get this smooth curve here in blue that's peaked at a population of 0.5, half the capacity of the field. And they're all those curves are peaked at a population of 0.5, half the capacity of the field. Because that's what the function xn times 1 minus xn looks like. The way to maximize that function is for xn to be a half. You get a half times a half. You get a half times 1 minus a half. So that's a half times a half. You get a quarter. And so that's the quarter here. You know, if you had a very small xn, then it's basically xn times 1, and you get a very small number. So it goes to 0. The function goes to 0 at xn as xn goes to 0. The function also goes to 0 as xn goes to 1, because as xn goes to 1, then 1 minus xn goes to 0. So the maximum value of the function here is a quarter at a population of a half, and it falls off to 0 at the two extremes of the population. And you can see here, this is why you can't physically have a reproduction rate of more than 4. Because if I had a reproduction rate of more than 4, then I could I would get a population greater than the capacity of the field. So that's why that range is limited in the studies that we'll do. Okay, I'm going to go to the code then. So this is a great example for, you know, computational physics and Python coding. So let's just now take a look at this. None of us know anything about ecology, and maybe you do. I don't know anything about ecology, but with this little difference equation, I built in two of the major features of reproduction and starvation, and we're just going to explore this model of population growth. So I'm going to go back to my drive here, and I've got this logistics map. This is called the logistics map, and I'm just going to look at a bunch of examples. Okay. I wanted to introduce, though, before I look at the examples, just one little additional bit of Python coding that I didn't mention last week, and I record that I'll want this week. And that we talked about native functions in Python last week, print is one. We talked about library functions, sine and cosine are ones, but you can also define your own functions in Python. And I wanted to define a function here that corresponds to calculating the next generation population from the current generation population. So that's a function I want to use. I want to define as a user, because I want to call that lots and lots of times. I'm going to call this literally thousands of times as I propagate my rabbit populations into the future. And so I didn't want to be writing out the equation, the logistics map every time. I just want to call a function. And that's in this second cell here. You know, the function is a simple function, right? It's the reproduction rate times the current population times the difference between the capacity population and the current population. So it's R times X times 1 minus X. There is the logistics map. I'm going to define a function. I'm going to call it logistic that I give the current population. It gives me the future population. That's what a function does. I call it with an angle and it gives me back the sign of the angle. Here I'm going to call it with the current population, going to give me back the future population. This is the format for defining your user functions. There's a keyword to say, I'm going to define my user function here. So that's the define here. Then if you've got a sine, cosine, exponential, log, you've got a name for the function. I need a name for my function, my user function. I call it logistic. With a sine or a cosine or an exponential, you have an argument or arguments to the functions, and I've got to have arguments here. The 2 arguments I'm going to make for the current population, that's the x here, and the reproduction rate, that's the parameter in the logistics map. So I'm passing in these 2 parameters. Then I've got the body of the code that is the function. And the body of my code is actually really rather simple. It's just this one line. And I want to return the result of that one line calculation of the future population. And I can do that return a value with the return statement. And the value I want to return, I just calculated it on that return statement. So I'm going to return reproduction rate times the current population. That's 1 minus the current population to give me the next generation's population. Every time now after I call the logistics map, I'm going to call that function. I'm going to be calculating the future population from the current one. So that's pretty handy. Yeah, okay, so now let's go on. We got a function just like sine or cosine that I can use. So here I'm going to say in this cell now, I'm going to start with a rabbit population and I'm going to look at how it evolves over 250 generations. So, you know, many generations, there will be tens of thousands of years, human lifetime. So generations is the number of generations I'm going to look at. And I'm going to put the generation populations into an array. So I can look at how the rabbits evolved over these 250 generations. So I'm defining an array here of this size generations. Zeros, like ones, is just a function in NumPy that you can use to define an array of zeros or ones. There's a parameter for my map, my logistics map, a reproduction rate. In this example, again, I'm going to use reproduction rate 0.7. It's less than 1. And I'm going to use an initial population of, let me make it, 0.05. So there's a small number of rabbits in a big field, that kind of situation. And then I'm going to make a loop where I just call the logistics map. The whole body of the code is in these 2 lines here. It's a loop over a sequence of generations from the 0th generation to the last but 1 generation, where I take the population for that particular current generation, that's I, so it's stored in this array here, And given that population for the current generation and the reproduction rate, I calculate the future generation. So this loop just fills up the population array with the evolving population over these 200 generations. And then I just plot it. You notice here that I only gave one variable to plot. I didn't say plot the generation number as the independent variable, and the population as the dependent variable. I just gave one parameter. If you just do that, it takes that one parameter as the dependent variable and plots it as a function of the array index of that dependent variable. And that is the generation number in this case. So that was just it saved me a moment in time in writing it out. It cost me time, I realized, and it's much more time in explaining what I did. But anyway, this is just a shortcut. So let's run that and see what we get. And look, we started with a reproduction rate of 0.7. So every rabbit has a child, 0.7 of a child. Well, we know what's going to happen. The rabbit population is going to die out. It's just going to take some time to die out. And that's what's shown on this plot, right? We started with a rabbit population of 0.05, so there's no problem with starvation, but they're just not reproducing fast enough. And so that over the span of 10 generations or so, they've died out, and rabbits go extinct. I got a bunch of cells that are just copies of that cell that made that plot, but I'm just changing a parameter each time I show you the cell. So there's nothing new about the cells other than I'm going to change the value, say, of R, the reproduction rate. Look, now I've changed the reproduction rate so that the each rabbit has 1.3 children. So now we think the rabbit population is going to grow. And indeed, the rabbit population does grow from the initial value of 0.05, grows and grows and grows. It doesn't just keep growing up to the maximum population. There's some sort of balance between, the capacity of the field and the reproduction rate that the population evolves to. So we see here that after some transitory period, there's just a stable population of rabbits that reproduce at that rate of 1.3. And it's a capacity that is about 0.22. Let's make these more reproductive rabbits in this cell, because they're reproducing at a reproduction rate of each rabbit here has 2.95 children, so they're producing almost 3 children for each rabbit. And we'll do the same calculation again. And look, they also, of course, survive. They're reproducing. They survive. They become a much larger stable population in the field, about 0.7 compared to about 0.2 for the lower reproduction rate. So there's the equilibrium population has a higher population based on this sort of starvation capacity versus reproduction equilibrium that emerges. There's still that transitory period. There's a little interesting period here where the population oscillates, like kind of a damped oscillator, but it equilibrates too, and you get a evolving population that just is constant. But then a really interesting thing happens when you go above 3. So this is a reproduction rate of 3.05. So just increase the population rate a little bit. You get a rapid rise in the population. you get some sort of transient, but a reproduction rate of 3.05, there's a periodicity to the population. Population goes up and down, up and down, up and down from generation to generation. There's two values for the population after the transitory period. And so there's like a bifurcation of the population. And that happened at 3.05. And so there's this bifurcation. And here in this one, I went to a 3.445. I'm being really careful picking these numbers now. Look what happened as you get to 3.445. There's a transition. And now you get a population that, again, there's a transitory period. Don't worry too much about this. But then there becomes a period where there's actually 4 different populations in here. The rabbit population is oscillating between. I think actually, sorry, I meant this one. That one was just before this second bifurcation. This one at 3.455 is after the second bifurcation. And then here you see at large times these 4 distinct populations. And this goes on and on and on and on, these bifurcations, until a certain reproduction rate, it just becomes chaos. And you get a reproduction rate that kind of looks like, let me show you. This is a reproduction rate of 3.75. And the 2 different colors here are 2 very, very slightly different reproduction rates, like slightly, I mean, different by a part in a million. So they're 3.75 plus or minus a part in a million, and they exhibit chaotic behavior. They're only different by a part in a million, but they have very different behavior. This is chaos. So chaos has got onset. All this is built in that simple, it's the most simple map of populations you could build based on reproduction and starvation. Right? That simple linear map, nonlinear map, exhibits the population increasing, the population becoming stable, the population oscillating with bifurcations, with period 2, period 4 generations, period 8 generations, and chaos. All that's built in that linear map. Okay. The homework is to make a plot of this bifurcation and this chaos and this starvation or extinction and these stable populations called a Feigenbaum plot. Let me just end up on the homework. Is to make a plot like this. So this is the homework assignment. On this plot, this is the reproduction rate. So on my plots, the horizontal axis was the number of generations. This is now the reproduction rate. And so I'm making this plot by running up a whole range of reproduction rates. And here, vertically, is the populations for each of these reproduction rates for a number of generations. This point here, for example, is actually 100 points on top of one another for the 1001 to 1100th generations. So there's 100 points here. There's 100 points here. Any other reproduction rate, there's 100 points. I generated this with, I think, 100 different reproduction rates. So this is a scatter plot that contains 100 times 100 data points. This is the classic plot that shows these effects of extinction, stable populations, bifurcation of populations, period 2 doubling, period 4 doubling, period 8 doubling, and then finally chaos.